It begins in silence, deep beneath the surface of the Earth, in a place where temperatures reach thousands of degrees and pressure would crush a human body in an instant. Something extraordinary has been forming for billions of years. Carbon, the same element that builds trees, fuels stars, and forms the backbone of life, has been pressed and shaped by forces beyond comprehension. Out of this invisible furnace emerges a material so brilliant, so enduring, that it has captured both human imagination and scientific ambition: the diamond. For centuries, diamonds have symbolized wealth, power, and eternity. They've adorned crowns, marked lifelong commitments, and inspired legends of curses and miracles. Their flawless transparency and extraordinary hardness made them precious objects, but also mysterious ones. Few stop to ask, what else could they do? What lies behind the sparkle, not in myth, but in physics, chemistry, and the very fabric of the cosmos? The answer, it turns out, is far stranger and more revolutionary than anyone in the jewelry trade could have imagined. Locked inside each glittering stone is a combination of properties unlike any other substance on Earth: unmatched thermal conductivity, exceptional optical clarity, and, in some rare cases, the ability to conduct electricity. For most of human history, these traits went unnoticed or unused. But in the last few decades, scientists began to look beyond the gem, to see diamonds not as ornaments, but as tools. As the 21st century accelerates, diamonds are no longer just geological wonders. They are becoming technological frontiers. This is the dawn of what some researchers now call the new diamond age. Laboratories around the world are racing to do something once thought impossible. Not just to copy nature's diamonds, but to surpass them, to build super diamonds. These are synthetic stones engineered to be tougher, larger, purer, and more versatile than anything dug from the ground. In their transparent lattices lies the promise of a future where computers run faster than ever imagined, where spacecraft survive the harshest cosmic conditions, and where the boundaries between natural and artificial blur into something entirely new. But to reach that future, science must confront a paradox. Diamonds are formed over billions of years under conditions nearly impossible to replicate: crushing pressures deep within the Earth's mantle and unimaginable temperatures. They are born from the death of stars, forged in supernova explosions, and carried across space before being locked beneath our planet's crust. To make a better diamond, humanity must not only mimic nature's ancient process but outdo it. That means creating in days what the cosmos took eons to produce, and doing it in shapes and sizes that nature never intended. The story of super diamonds is not merely a tale of material science. It is a story that stretches from the hearts of dying stars to high-tech clean rooms, from museum vaults holding priceless blue gems to military laboratories pushing the limits of physics. It involves the deep past and the distant future. It is both cosmic and intensely human, driven by curiosity, ambition, and the relentless pursuit of mastery over the elements. Imagine a future where your smartphone contains a wafer of synthetic diamond that keeps it cool no matter how much power it uses, where satellites are shielded by transparent diamond windows capable of withstanding space's brutal radiation, where lasers are guided through diamond lenses, and medical tools are sharper than anything ever forged in steel. Imagine machines that run on diamond instead of silicon, devices that are smaller, faster, and nearly indestructible. Sounds like science fiction. Yet, in laboratories in Washington, Johannesburg, and Florida, this future is already being built. By using techniques like chemical vapor deposition, scientists can now grow diamonds molecule by molecule inside vacuum chambers. By seeding tiny crystals and bombarding them with gases at thousands of degrees, they are coaxing carbon atoms into arranging themselves into perfect lattices. Within hours, a microscopic seed can double in size. Within days, entire sheets of diamond can emerge, ready to be shaped into electronic wafers or precision instruments. And that's only the beginning. Researchers are now drawing inspiration from an even stranger source: space itself. By studying rare black diamonds called carbonado, believed to have formed in supernova explosions and fallen to Earth on meteorites, scientists have discovered new ways to make diamonds tougher and larger than ever before. Instead of using immense pressure, they can now grow multicrystal structures in low-pressure environments, mimicking the vacuum of space. The result is a material that is not only harder than any natural diamond but also more resistant to breaking, capable of being molded into shapes nature never produced. This unfolding scientific revolution raises a profound question. What happens when humanity learns not only to replicate the most perfect material nature has ever made, but to improve it? The implications are staggering. Superdiamonds could disrupt entire industries, from microelectronics to aerospace, from energy to defense. They could enable technologies that rewrite what's possible in computing, communication, and exploration. And yet, their rise is tied to some of the oldest stories in the universe, stories written in the light of dying stars. This is the story we're about to uncover. A story that begins 4 billion years ago, in the heart of a red giant star, and stretches forward into the next technological age. A story where geology, astrophysics, and human ingenuity converge. Welcome to the age of superdiamonds, where the line between cosmic history and human invention begins to disappear. Part 1. The first clues beneath the surface. The story begins not in a laboratory, but in the ground itself. In the late 19th century, prospectors scouring the rugged landscapes of South Africa stumbled upon something that would change both global economies and scientific curiosity forever. Glinting within the rough, volcanic rocks were small, translucent crystals unlike anything they had seen before. These were diamonds, and their sudden appearance sparked a frenzy. Entire towns rose from the dust as miners tunneled deep into the earth, driven by greed, ambition, and the promise of unimaginable wealth. But beneath the feverish rush for profit, a quieter group of observers noticed something puzzling. The diamonds weren't scattered randomly. They appeared in clusters, often concentrated in carrot-shaped pipes that seemed to pierce upward from deep within the earth. Each discovery led to another nearby, suggesting a hidden geological pattern. Early geologists speculated that these pipes were ancient volcanic structures, conduits through which the diamonds had been transported from somewhere far below. They named the rock hosting these crystals kimberlite, after the town of Kimberley, where some of the first major diamond finds occurred. At the time, no one fully understood where diamonds came from. Some believed they had condensed from mysterious vapors within the Earth's crust. Others imagined they were the product of lightning strikes or alchemical transformations underground. The truth, as science would later reveal, was far more extraordinary and much deeper. In the early 20th century, geologists began to trace the journey of diamonds back to their origins. By examining the composition of kimberlite and the crystals trapped within it, they found evidence pointing toward extreme pressures and temperatures far beneath the crust. Diamonds, it turned out, were born not near the surface, but in a hidden zone called the mantle, roughly 100 miles deep. Down there, temperatures soar above 2,700 degrees Fahrenheit, and the crushing pressure is equivalent to the weight of thousands of grown men standing on a single foot. In this brutal environment, ordinary carbon atoms, the same kind found in graphite pencils, are forced into a rigid lattice structure. Over millions of years, the structure transforms soft, black carbon into clear, indestructible diamond. The diamond's journey doesn't end there. They must somehow make their way from the mantle to the surface without disintegrating. This is where kimberlite enters the story again. During rare, violent eruptions, kimberlite magma rockets upward at incredible speeds, carving narrow, carrot-like pipes through the rock layers. Embedded within this molten conveyor belt are diamonds, carried from their secret vaults deep underground to the surface in a geological instant. Once cooled, the magma hardens, locking the crystals in place for miners to find centuries later. These discoveries solved one mystery but opened another. If diamonds are forged under such extreme and specific conditions, could humanity ever hope to replicate their creation? Early attempts seemed futile. Reaching the necessary pressures and temperatures was beyond the capabilities of any existing technology. For decades, diamonds remained objects to be found, not made. Yet whispers of possibility began to circulate. By the mid-20th century, as industries demanded harder, more durable materials for drilling, cutting, and machining, scientists and engineers started asking a daring question. Could we create diamonds ourselves? Not in eons, but in months, weeks, or even days. The first major attempt to answer this question came in the 1950s at General Electric, under a secretive initiative known as Project Superpressure. In a series of carefully controlled experiments, GE scientists placed pure graphite, carbon's most common form, into enormous hydraulic presses. They then subjected it to pressures approaching 800,000 pounds per square inch and temperatures above 2,500 degrees Fahrenheit, conditions meant to mimic the depths of the mantle. The process was complex, dangerous, and expensive. 5 years and millions of dollars later, the team announced a historic breakthrough: the creation of the world's first synthetic diamond. These early diamonds were small and imperfect, more suited for industrial drills than engagement rings. But their existence shattered a psychological barrier. Diamonds were no longer the exclusive product of nature's hidden forges. They could be born in human-built machines. A door had opened, one that scientists would spend the next half-century widening. Meanwhile, as technology advanced, another line of inquiry emerged. If we could understand where diamonds came from on Earth, perhaps we could learn more by looking beyond it. Some of the carbon that eventually forms diamonds doesn't originate in the mantle at all. It comes from stars. In astrophysical laboratories, researchers studied the life cycles of stars and found that carbon is forged in the final stages of stellar evolution. When a massive star approaches death, it swells into a red giant, fuses helium into carbon, and eventually explodes in a supernova. The blast scatters carbon atoms across the cosmos, seeding future planets and, ultimately, the raw material for diamonds. This cosmic revelation gave the diamond story an unexpected dimension. These crystals were not merely geological artifacts. They were remnants of stars, forged in stellar furnaces billions of years ago and delivered to Earth by violent cosmic events. Every diamond found in the ground carries within it a fragment of celestial history. In the late 20th century, the search for diamonds expanded to unexpected places. Strange, black, porous stones called carbonado began to attract attention. Found in parts of South America and Central Africa, these black diamonds did not fit the profile of ordinary mantle-formed gems. They lacked the telltale single-crystal structure and were riddled with tiny holes. Upon closer study, scientists concluded that carbonado likely formed in space, not underground. They appear to be aggregates of countless tiny diamond crystals that fused together in low-pressure cosmic environments, possibly during supernova explosions. Later, they were delivered to Earth by meteorites. This discovery stunned researchers. For the first time, they had physical evidence of diamonds formed outside our planet, under entirely different conditions. And these spaceborne diamonds weren't just geological curiosities. Their multi-crystal structure made them tougher and harder to break than their earthly counterparts. Carbonado diamonds hinted at entirely new ways of forming super-strong materials without relying on impossible pressures. By the dawn of the 21st century, the story had expanded from mines and laboratories to the stars themselves. Scientists were now piecing together a vast, interconnected narrative. Diamonds born in dying suns, transformed in Earth's mantle, carried upward through volcanic eruptions, and finally unearthed by human hands. This narrative contained both a challenge and an opportunity. If nature could produce diamonds through cosmic violence and deep earth pressure, could human ingenuity find a shortcut? A way to build super diamonds better, faster, and cheaper than the cosmos ever could? The first clues had been unearthed. The pipes of kimberlite, the hydraulic presses of General Electric, the black meteorite diamonds from space. Together they sketched the outline of a mystery that scientists were now determined to solve. Part 2. Unlocking the hidden powers for most of human history. Diamonds were valued for one thing: their beauty. Their optical clarity and hardness made them perfect for jewelry, but their deeper physical properties remained largely unexplored. In the 20th century, that began to change. Scientists discovered that diamonds possessed a set of characteristics unlike any other substance on Earth. characteristics that could redefine the technological landscape if they could only be controlled and harnessed. Diamonds are, first and foremost, hard. Not just a little harder, but in a category of their own. On the Mohs scale of mineral hardness, diamond sits at the top, 4 times harder than corundum, the mineral that makes up sapphires and rubies. This extraordinary hardness comes from the way carbon atoms are arranged in the diamond lattice. Each atom bonds with 4 others in a 3-dimensional network, creating a structure that resists deformation in every direction. Graphite, by contrast, consists of sheets of atoms bonded in flat planes, which slide easily against one another. The difference between pencil lead and diamond is purely structural, and it makes all the difference. But hardness is just the beginning. Diamonds are chemically inert. They resist corrosion, even in harsh environments. They are optically transparent across an unusually wide spectrum, from ultraviolet to infrared. This makes them not only visually stunning but also ideal for optical technologies that require materials capable of transmitting light without distortion. Unlike glass, diamonds don't significantly alter the light that passes through them, making them perfect candidates for advanced lenses and windows. And then came the property that surprised even seasoned physicists: thermal conductivity. Diamonds conduct heat better than any known material, about 5 times better than copper. This means that a diamond can carry heat away from a hot spot almost instantaneously, remaining cool even under intense energy loads. For electronics, where heat buildup is a major limiting factor, this property is revolutionary. Imagine a chip that doesn't need a fan, a processor that runs without overheating, or a laser system that stays stable under immense power. Perhaps the most unexpected discovery, however, came from studying a single famous stone: the Hope Diamond, kept in the Smithsonian Institution in Washington, D.C. This deep blue gem, weighing over 45 carats and worth hundreds of millions of dollars, had long been surrounded by myth and superstition. Tales of a curse followed it from India to Europe and finally to the United States. But in the laboratory, scientists found something far more fascinating than any legend. When exposed to ultraviolet light, the Hope Diamond glows with an intense orange-red phosphorescence that lingers for minutes after the light is turned off. For centuries, this glow was attributed to mystical forces or curses. Modern spectroscopy told a different story. By analyzing the wavelengths of light emitted, scientists identified 2 key impurities inside the diamond lattice: boron and nitrogen. The combination of these 2 elements explains the gem's unique behavior. Boron makes the diamond blue. Nitrogen interacts with boron to produce the red afterglow. It was not magic, but atomic structure that gave the Hope Diamond its spectral signature. Boron does more than change a diamond's color. It also turns a diamond into a semiconductor. Pure white diamonds, made of only carbon, are electrical insulators. Electricity simply doesn't flow through them. But in boron-rich blue diamonds like the Hope, the extra atoms interact with the lattice in such a way that electrons can move, allowing the stone to conduct electricity. This discovery transformed the way scientists thought about diamonds. They were no longer just inert, decorative stones. They were potential components for advanced electronics, capable of both conducting electricity and dissipating heat, 2 properties rarely found together. For decades, silicon had been the undisputed king of the semiconductor world. From the first transistors in the 1950s to the microchips powering modern computers, silicon defined the technological age. But silicon has a weakness: it overheats easily. As more power flows through silicon chips, they require elaborate cooling systems to keep temperatures below about 300 degrees Fahrenheit. Push beyond that and the circuits fail. This limitation is one of the biggest bottlenecks in modern computing. Diamonds, by contrast, can withstand temperatures exceeding 1,800 degrees Fahrenheit without breaking down. They can carry 30 times more power than silicon and operate up to 3 times faster. In theory, a diamond-based chip could run at extreme speeds with minimal cooling, revolutionizing everything from smartphones to spacecraft. But there was a catch. Natural diamonds with the right properties were incredibly rare. Blue boron-rich diamonds like the Hope appear in nature only once in every 100,000 stones, and they almost never form in the convenient shapes needed for electronic devices. This scarcity created a scientific puzzle. If diamonds are so promising, why weren't they already powering the world's technology? The answer lay in supply and shape. Natural diamonds are irregular, expensive, and difficult to modify. To unleash their hidden powers, scientists would need a way to grow diamonds on demand, in forms tailored to specific technological needs. The implications of solving this puzzle were staggering. If diamond wafers could be produced like silicon wafers, the entire electronics industry could be transformed. Imagine wafer-thin sheets of diamond, etched with microcircuits, mounted in laptops and satellites. Such materials would not only make devices faster and more energy efficient, but also vastly more durable, capable of surviving extreme environments from deep space to combat zones. By the 1990s, research laboratories around the world were beginning to take this idea seriously. Advances in high-pressure, high-temperature techniques, combined with new chemical methods, suggested that it might be possible to grow synthetic diamonds with controlled impurities, diamonds engineered not for sparkle but for function. The question was no longer whether diamonds could revolutionize technology. It was how soon. Parallel to this scientific awakening was a shift in mindset. For centuries, diamonds had been treated as geological treasures, objects to be extracted and polished. Now they were being reimagined as platforms for innovation, materials whose real value lay not in their rarity but in their extraordinary physical properties. This was a subtle but profound transformation. It required chemists, physicists, engineers, and astrophysicists to collaborate in ways they never had before, to see diamonds as not merely ancient stones but future tools. The Hope diamond's orange-red glow, once thought to be a curse, became a symbol of this new era. It was evidence that inside the seemingly inert carbon lattice, remarkable behaviors awaited those who looked closely enough. Diamonds were not passive relics of the Earth's mantle. They were active participants in the future of technology. As the 20th century drew to a close, the race to unlock these hidden powers was accelerating. New machines, new techniques, and new ideas were converging. If nature could make diamonds in the crushing darkness of the mantle, perhaps humans could make something even better, not through superstition or luck, but through precision and design. The age of the diamond as ornament was ending. The age of the diamond as engineered material was about to begin. Part 3, Building a Better Diamond. By the time the 20th century reached its midpoint, the world was shifting. The jet age was beginning, nuclear physics was reshaping global power, and the transistor was poised to ignite a computing revolution. Against this backdrop, a small team of engineers at General Electric began working on a challenge that sounded almost mythic: to build a diamond from scratch. Diamonds had always been the ultimate benchmark of natural perfection. They were the hardest substance known, born from crushing pressures and searing temperatures deep inside the Earth. For scientists in the 1950s, the idea of reproducing such forces in a laboratory seemed closer to science fiction than industrial research. Yet G believed it could be done. The project was kept secret under the codename Project Superpressure. At its core was a simple but formidable idea. If diamonds form from carbon under high pressure and temperature, then perhaps carbon could be transformed into diamond inside a machine built to mimic the Earth's mantle. The materials of choice were pure graphite powder and a small metal catalyst, placed inside a specially designed hydraulic press capable of generating unprecedented force. These presses, massive steel giants, squeezed the graphite at pressures approaching 800,000 pounds per square inch, roughly equivalent to supporting 20 sedan cars on a single square inch of material. Simultaneously, the sample was heated to more than 2,500 degrees Fahrenheit, reproducing the extreme conditions found 100 miles beneath the Earth's surface. For years, attempts failed. The graphite would either burn, deform, or fail to convert. But in February 1955, after 5 years of work and millions of dollars, the team finally succeeded. For the first time in history, a synthetic diamond emerged from a man-made machine. The product was not a sparkling gemstone. but a tiny, gritty crystal, small, yellowish, and irregular. It was not destined for a jewelry case but for industrial tools. Yet its significance was monumental. Humanity had recreated, in days, a process that nature required billions of years to perfect. It was proof that diamonds were not the exclusive gift of geology. They could be engineered. This breakthrough triggered a wave of innovation. Laboratories in the United States, Europe, and later Asia began experimenting with their own high-pressure, high-temperature, HPHT techniques. By the late 20th century, synthetic industrial diamonds had become essential components in cutting, grinding, and drilling technologies. Their extraordinary hardness allowed industries to bore through granite, shape metals with precision, and extract oil and gas more efficiently. For decades, these small, man-made stones quietly revolutionized heavy industry. But they were still limited in scope. HPHT diamonds were typically small, irregular, and produced in batches. They couldn't be shaped easily into large, flawless wafers or tailored electronic components. They were industrial workhorses, not technological game-changers. To move beyond their role as cutting tools, scientists needed a method that could grow diamonds larger, faster, and with unprecedented control. This next step came from an unexpected source: space. In the late 20th century, geologists studying strange black diamonds called carbonado made a startling discovery. Unlike traditional diamonds, which form as single, flawless crystals under immense pressure, carbonado consists of countless microscopic diamond grains fused together. It is riddled with tiny holes and impurities, giving it a charcoal-like appearance. Found in South America and Central Africa, carbonado puzzled scientists for decades. It didn't seem to come from the Earth's mantle at all. The breakthrough came when researchers analyzed its isotopic composition and internal structure. Carbonado lacked the high-pressure signatures of mantle formation. Instead, it appeared to have formed in low-pressure environments, likely in the vacuum of space. The leading theory proposed that these diamonds originated in supernova explosions, the death throes of massive stars. In these violent cosmic events, carbon atoms collide and fuse in space, forming vast clouds of microscopic diamonds. Over time, these clusters aggregate, stick together, and are eventually transported to Earth aboard meteorites. When a meteorite carrying carbonado hits Earth, it showers black diamonds across the landscape, a cosmic delivery of super-tough, multi-crystal structures unlike anything formed underground. These diamonds are so tough that they're nearly impossible to cut along cleavage planes, a weakness that plagues natural single-crystal gems. Their structure makes them ideal candidates for ultra-durable materials. This cosmic insight led scientists to rethink how diamonds might be grown. If diamonds could form in space, under low pressure and in vacuum, perhaps the key to building a better diamond wasn't to push harder, but to think differently. In the 1980s and 1990s, researchers developed a new technique that would revolutionize synthetic diamond production: chemical vapor deposition, CVD. Instead of crushing graphite under immense pressure, CVD uses a vacuum chamber and a controlled gas environment to grow diamonds atom by atom. The process begins with a diamond seed, a tiny crystal placed inside a chamber heated to around 3,600 degrees Fahrenheit. A mixture of methane, a carbon-bearing gas, and hydrogen is introduced. Microwaves bombard the gases, stripping away hydrogen atoms and liberating carbon atoms. These carbon atoms then settle onto the diamond seed, bonding to its lattice and gradually building up a larger crystal. The process is mesmerizing. Within 24 hours, the seed can double in size. Over several days, scientists can grow wafer-thin sheets of diamond up to 8 inches wide, or large crystals 3 times bigger than the original seed. Unlike HPHT methods, CVD allows for precise control of impurities and structure. Engineers can intentionally introduce boron to create semiconducting blue diamonds, or maintain pure carbon for insulating transparent layers. For the first time, it became possible to design diamonds with specific properties, not merely accept what nature provided. CVD opened the door to new applications. At the U.S. Naval Research Laboratory, for example, scientists began growing diamond wafers on silicon substrates, using a salt shaker technique to seed thousands of tiny diamonds across a surface. As these grew, they fused into a continuous sheet of multicrystal diamond. These sheets were tougher than natural diamonds, electrically tunable and thermally unmatched. They could potentially replace silicon in microchips, offering unparalleled speed and heat resistance. Meanwhile, private companies joined the race. In Sarasota, Florida, the company Genesis pioneered machines that could grow large synthetic diamonds by feeding graphite into diamond seeds under controlled HPHT-CVD hybrid conditions. Their goal wasn't jewelry, but high-tech components. Genesis and similar companies envisioned a future where diamond wafers could be mass-produced for electronics, optics, and even defense applications. By the turn of the 21st century, scientists were no longer merely imitating nature. They were surpassing it. Nature could take billions of years to form a gem deep underground. Humans could now create tougher, purer, more functional diamonds in a matter of days, and shape them into forms that the planet never could. But with this leap forward came new questions. How far could synthetic diamond technology go? Could diamond wafers truly replace silicon at the heart of modern electronics? Could carbonado-like multicrystal structures give rise to a new class of supermaterials? And, perhaps most intriguingly, what new frontiers would open once humans mastered the ability to grow one of the universe's most remarkable substances at will? The race to build a better diamond had moved from mines to machines, from deep earth to vacuum chambers. What began as a geological mystery was becoming a technological revolution, one that would soon stretch far beyond laboratories, reshaping industries and possibilities on a planetary scale. Part 4. Beyond Silicon. The new technological frontier for half a century, silicon has been the beating heart of the modern world. From the first bulky transistors of the 1950s to today's ultra-thin smartphones and global data networks, silicon made the digital age possible. It is abundant, easy to process, and can be engineered into intricate microchips that power everything from laptops to satellites. Entire industries and cities, most famously California's Silicon Valley, rose around this single element. But even as silicon transformed human civilization, its limitations were becoming increasingly clear. Silicon is a semiconductor, but it struggles under stress. As circuits shrink and power demands grow, silicon chips overheat. Beyond around 300 degrees Fahrenheit, they fail. This is why your laptop needs a fan, why data centers consume staggering amounts of energy for cooling, and why high-performance computing systems face an invisible ceiling. The more power you push through silicon, the hotter it gets. The hotter it gets, the less stable it becomes. For decades, engineers compensated with clever designs. Heat sinks, fans, liquid cooling, and materials that draw heat away from the chip. But these were stopgaps, not solutions. As transistors approach atomic scales and devices require exponentially more power, silicon's fundamental thermal limitations have become a barrier to progress. And this is where diamond enters the story, not as jewelry, but as a radical alternative. Synthetic diamond wafers grown through chemical vapor deposition and hybrid techniques have extraordinary thermal conductivity, 5 times greater than copper, the metal traditionally used for heat dissipation. More than that, they are electrically tunable. By introducing trace elements like boron, scientists can make diamond conduct electricity, behaving like a semiconductor. By keeping it pure, they can make it act as an insulator. This duality is rare and powerful. Imagine a single material that can channel heat like a superconductor, insulate like glass, or carry current like a high-performance chip, depending only on how you grow it. That's what diamond offers. The numbers are staggering. Diamond can operate at temperatures exceeding 1,800 degrees Fahrenheit, carry 30 times more power than silicon, and run 3 times faster without failure. A diamond-based microchip could, in theory, function in the vacuum of space, in the blistering heat of a jet engine, or in the heart of a battlefield without a fan or cooling system. But thermal performance is only part of the story. Diamond's mechanical toughness far exceeds silicon's. Silicon wafers are brittle, A minor crack can ruin an entire production run. Diamond wafers, especially multicrystal sheets inspired by carbonado structures, are tougher, more resistant to fracture, and capable of being shaped into thin, flexible forms. This resilience opens the door to applications that would destroy conventional electronics. The U.S. Naval Research Laboratory was one of the first to explore these possibilities seriously. Their engineers seeded silicon wafers with countless tiny diamond crystals and grew them into continuous diamond layers. These hybrid diamond-silicon wafers were then subjected to extreme thermal and electrical stress. Where silicon alone would have cracked or failed, the diamond layers held firm, conducting heat away almost instantly. The results were so promising that military researchers began envisioning diamond-based systems for radar, communications, and defense electronics, where reliability in harsh conditions is paramount. Meanwhile, civilian applications were equally tantalizing. Think of data centers, where thousands of servers generate immense heat, requiring complex cooling systems that consume nearly as much power as the servers themselves. Replacing silicon with diamond could slash energy costs, reduce environmental impact, and enable more compact designs. In consumer electronics, diamond chips could make smartphones and laptops run cooler, last longer, and process data at unprecedented speeds. Another promising field is space exploration. Electronics aboard spacecraft face brutal temperature extremes and radiation levels that would fry most terrestrial devices. Diamond's resilience, transparency to a wide spectrum of radiation, and ability to function at high temperatures make it ideal for sensors, communication arrays, and control systems that can survive the vacuum of space without heavy shielding. Even optics stand to be transformed. Diamond's unmatched transparency across ultraviolet, visible, and infrared wavelengths means it can serve as optical windows for lasers, telescopes, and high-energy instruments. Where glass would warp or shatter under stress, diamond windows remain stable, transmitting light with minimal distortion. For high-powered laser systems, where heat buildup can warp even the best quartz lenses, diamond could be the perfect solution. The potential applications cascade outward like a chain reaction. Automotive industries could use diamond electronics to build ultra-efficient electric vehicles resistant to thermal failure. Medical tools could incorporate diamond-tipped or diamond-guided precision instruments, sharper and more durable than steel. Telecommunications could harness diamond's properties to build ultra-fast, energy-efficient networks. Yet for all this promise, there are still obstacles. Producing large, flawless diamond wafers remains challenging and expensive, though costs have fallen dramatically since the early 2000s. The technology for growing multi-inch diamond sheets using CVD is advancing rapidly, but scaling up for mass production requires new infrastructure and techniques. Unlike silicon, which is easily sliced from ingots, diamond must be grown, a slower process that demands meticulous control. Another challenge lies in integration. Modern electronics are deeply intertwined with silicon fabrication processes. Entire industries rely on decades of silicon-based expertise, equipment, and design. Shifting to diamond isn't just a materials upgrade, it's a paradigm shift. Fabrication methods must evolve, new doping techniques must be perfected, and designers must rethink circuits from the ground up to exploit diamond's unique properties. Despite these hurdles, momentum is building. Government research agencies, private companies, and academic institutions have invested heavily in diamond electronics. Startups envision diamond chips powering next-generation AI processors. Defense departments see them enabling more robust systems in extreme environments. Space agencies view them as a cornerstone for deep space missions where maintenance is impossible. And then there's speed. Diamond chips could theoretically operate at frequencies far beyond what silicon can handle. Traditional silicon transistors begin to lose efficiency as frequencies climb into the tens of gigahertz. Diamond's superior thermal and electronic properties allow for operation at frequencies hundreds of times higher, enabling technologies that today remain in the realm of speculation: instantaneous wireless networks, real-time global computation, or sensors capable of detecting the faintest cosmic signals. It's no wonder that many scientists and engineers describe this period as the threshold of a new technological era. Just as silicon once displaced vacuum tubes, diamond may soon displace silicon, not through marketing or hype, but through sheer performance. The new diamond age is not a poetic metaphor. It's a very real, emerging possibility. In laboratories today, wafer-thin sheets of synthetic diamond are already being tested in circuits, lasers, and high-power devices. Their behavior under stress is rewriting engineering assumptions long held as immutable. What was once the stuff of geological wonder and cosmic history is now a frontier of human invention. But this frontier comes with its own questions. If diamonds can truly replace silicon, how will industries adapt? How will economies shift when a material once associated with luxury becomes a foundation of global infrastructure? And what new technologies, perhaps ones we can't even imagine, will arise when the world's most perfect material becomes as common in electronics as it once was in engagement rings? The answers to these questions are not far off. In fact, the first signs of this transformation are already appearing in specialized laboratories and niche industries. What remains is the leap from potential to reality. Part 5. The Science Behind the Spark. Atomic Secrets of Diamond. To understand why diamond is unlike any other material on Earth, you have to shrink your perspective, not just to the scale of molecules, but to atoms themselves. Diamonds are not extraordinary because of some mysterious energy. They're extraordinary because of the way carbon atoms arrange themselves when forced into a particular structure. It's a story written in the geometry of bonds, in the balance between pressure, temperature, and time. At its core, diamond is pure carbon, one of the most abundant and versatile elements in the universe. Carbon forms the backbone of life, the basis of organic chemistry, and the structure of countless compounds that make up planets, stars, and living things. What makes carbon special is its ability to bond in multiple ways. A single carbon atom has 4 electrons in its outer shell, allowing it to form up to 4 covalent bonds with other atoms. This flexibility gives rise to dramatically different structures, most notably graphite and diamond. In graphite, carbon atoms bond in flat, hexagonal sheets. Each atom connects to 3 neighbors, forming strong bonds within each plane but weak forces between layers. That's why graphite is soft. The sheets slide easily over one another, leaving marks on paper. In diamond, however, each carbon atom bonds to 4 others in a perfect 3-dimensional tetrahedral lattice. This structure is rigid in every direction, with no planes of weakness. It's what makes diamond so hard that it can cut through any natural material, and why it resists deformation even under immense stress. But how do carbon atoms adopt this structure in the first place? Nature achieves it through a precise combination of temperature and pressure, typically deep within the Earth's mantle. Around 100 miles below the surface, temperatures exceed 1,500 degrees Celsius (2,700 degrees Fahrenheit), and pressures reach roughly 50 kilobars, equivalent to millions of pounds per square inch. Under these extreme conditions, carbon atoms are squeezed so tightly that they rearrange into the diamond lattice, locking into place like a 3-dimensional scaffold. The formation process is ancient and slow. Most natural diamonds began their journey more than 3 billion years ago, during Earth's early history when tectonic activity and internal heat were far more intense than today. Once formed, the diamonds sat hidden for eons, buried deep in the mantle. Their ascent to the surface came through rare, violent kimberlite eruptions, geological rockets that blasted diamonds upward in a geological instant, trapping them in carrot-shaped pipes of volcanic rock. Without these eruptions, diamonds would remain entombed forever, inaccessible to human hands. For scientists hoping to make super diamonds, this deep Earth story is more than geological trivia. It's a blueprint. If diamonds form at specific pressures and temperatures, then perhaps those conditions can be replicated in the lab. That was the insight behind high-pressure, high-temperature, HPHT, synthesis, which used massive presses to crush graphite and heat it until carbon atoms snapped into diamond formation. The success of HPHT in the 1950s proved that the lattice could be built outside of the mantle, but it also revealed how delicate the balance is. Too little pressure, and the atoms remain in graphite's soft planes. Too much heat without the right environment, and the structure collapses before it forms. The atomic structure of diamond doesn't just explain its hardness. It also underpins its thermal, optical, and electronic properties, each rooted in the way electrons behave within the lattice. Take thermal conductivity, for example. In most materials, heat is carried by vibrations of the atomic lattice called phonons. The more disorder in the lattice, the more these vibrations scatter, reducing conductivity. Diamond's perfectly ordered lattice allows phonons to travel vast distances without scattering, making it the best-known heat conductor. Heat spreads through diamond like ripples across a perfectly still pond. Diamond's optical clarity stems from a similar perfection. Most materials absorb or scatter light at certain wavelengths, but diamond's tight, uniform bonds leave few defects for light to interact with. As a result, it's transparent across a vast range of the electromagnetic spectrum, from ultraviolet through visible light to infrared. Light slows down as it passes through the dense lattice, bouncing internally in complex patterns. This internal reflection is what gives cut diamonds their famous sparkle. But in technological applications, it means diamond windows and lenses can transmit light with minimal distortion under extreme conditions. Perhaps the most surprising property lies in diamond's electronic structure. Pure diamond is an excellent electrical insulator. Electrons are tightly bound in their covalent bonds, leaving no free charges to carry current. But introduce just a trace amount of boron, and everything changes. Boron atoms fit into the lattice and create holes that allow electrons to move, turning diamond into a p-type semiconductor. This is the secret behind the blue color of boron-rich diamonds like the Hope diamond and their ability to conduct electricity. This dual nature, insulator when pure, semiconductor when doped, makes diamond unique. Silicon can only be a semiconductor. Glass can only be an insulator. Diamond can switch between these roles depending on its atomic makeup. Engineers can grow a layer of insulating diamond, then deposit a thin boron-doped layer to conduct current, then add another insulating layer, all within the same crystal system. This opens possibilities for monolithic devices that are smaller, faster, and more efficient than anything silicon can achieve. The cosmic dimension of diamond structure deepens the story even further. Carbon itself didn't originate on Earth. It was forged in stars. Early in the universe's history, there was no carbon, only hydrogen, helium, and traces of lithium. Carbon was born in the hearts of aging red giant stars, where helium nuclei fused into carbon atoms. When these stars died, they exploded as supernovae, scattering carbon across the galaxy. Some of this carbon drifted through space, eventually gathering into clouds that formed new stars and planets, including Earth. In some cases, carbon formed tiny diamonds directly in space, under low-pressure conditions unlike anything found in the mantle. These cosmic diamonds, such as the mysterious carbonado stones found in South America and Africa, have a multi-crystal structure formed when countless microscopic diamonds collided and fused in the vacuum of space. Their structure is tougher than natural single-crystal diamonds and inspired scientists to rethink diamond synthesis. If the universe can make diamonds without pressure, perhaps humans can, too. This idea led to chemical vapor deposition, CVD, a technique that bypasses the need for extreme pressures altogether. Instead of squeezing carbon, scientists energize it, flooding a vacuum chamber with methane and hydrogen and bombarding the gas with microwaves. This agitation strips carbon atoms from the gas, which then settle onto a diamond seed and self-assemble into a lattice. In effect, the atoms are tricked into finding the diamond configuration because it's the most stable structure available in that environment. CVD doesn't just replicate nature, it improves upon it. Where natural diamonds are limited in size, shape, and purity, CVD allows engineers to control every variable: growth rate, impurity levels, crystal orientation. They can grow wafer-thin sheets, large single crystals, or carbonado-like multi-crystal structures, all tailored to specific applications. In a sense, scientists have learned to speak the language of carbon atoms, coaxing them into the precise arrangements needed for 21st-century technology. Understanding these atomic secrets has transformed diamond from a geological curiosity into a platform for innovation. Where miners once dug into the earth searching for rare gems, engineers now grow their own, atom by atom, with far more precision than nature ever allowed. And as they do, the boundary between the cosmic past and technological future grows thinner. Every synthetic diamond is both a product of human ingenuity and a continuation of processes that began in the hearts of ancient stars. The brilliance of diamond is no longer just something you see when light hits a cut stone. It's something hidden in its structure, waiting to be harnessed. Part 6. From Laboratories to Industries. Scaling the diamond revolution. The leap from scientific discovery to industrial transformation is never simple. In the case of synthetic diamonds, it has been both a technological race and a strategic gamble. What began as small, carefully controlled laboratory experiments in the mid-20th century is now expanding into multi-billion-dollar industries aiming to reshape electronics, energy, optics, and defense. But the road to this new diamond age has been anything but linear. In the early years of synthetic diamond research, production was slow and expensive. High-pressure, high-temperature presses could produce tiny crystals suitable for cutting tools, but not the large, flawless wafers needed for semiconductors or optical components. The chemical vapor deposition, CVD, method changed the game by allowing scientists to grow diamonds atom by atom inside vacuum chambers. Still, even CVD's early successes were confined to small research setups, machines that could grow 1 or 2 wafers at a time under carefully monitored conditions. The turning point came when research institutions began to pair advanced materials science with industrial engineering. Instead of growing diamonds as boutique laboratory products, companies started designing production lines that looked less like jewelry workshops and more like silicon wafer fabs. In Johannesburg, South Africa, a company named Element 6, a subsidiary of De Beers, became one of the first to scale diamond production for industrial use. Their facilities housed banks of massive HPHT presses capable of creating industrial diamonds in as little as 45 minutes. These were not gem-quality stones but super-hard crystals used for drilling, cutting, and grinding in industries from oil exploration to aerospace. By mass-producing these stones, Element 6 demonstrated that diamonds could be treated as engineering materials, not geological rarities. At the same time, in Sarasota, Florida, a company called Genesis pursued a different vision. Their goal wasn't just to make hard crystals for drills, but to grow large, high-purity diamonds suitable for electronics and optics. Using hybrid HPHT CVD systems, Genesis fed graphite into chambers containing tiny diamond seeds, gradually growing crystals that were 3 times larger than the seed in just a few days. Their engineers spoke not in carats but in growth rates, impurity concentrations, and crystal orientations. What had once taken nature billions of years could now be done in under a week. Meanwhile, government research institutions were laying the foundation for next-generation diamond electronics. At the U.S. Naval Research Laboratory in Washington, scientists perfected methods of seeding silicon wafers with thousands of microscopic diamond crystals, then growing them into continuous sheets through CVD. These diamond-on-silicon hybrids retained the electronic compatibility of silicon while adding diamonds' unrivaled thermal and mechanical properties. They were designed not for jewelry stores but for radar systems, high-power communications arrays, and aerospace instruments, where reliability under extreme conditions is essential. The Carnegie Institution for Science, also in Washington, pushed the boundaries further by using diamond in high-pressure experiments. Their scientists used diamond anvil cells, devices that squeeze tiny samples between 2 diamond tips, to recreate pressures found at the Earth's core. When the anvils shattered under unprecedented loads, researchers responded by growing ultra-hard superdiamonds through modified CVD methods, then exposing them to additional HPHT treatments to strengthen their structure. In just 6 days, they created a 15-carat superdiamond, 1/3 the size and 50% stronger than the legendary Hope diamond. This stone was not destined for display. It was a scientific tool, capable of generating pressures millions of times greater than atmospheric levels. Such breakthroughs began to attract serious attention from industries far beyond mining and gem cutting. Semiconductor companies, long dependent on silicon, started funding research into diamond wafers that could handle higher power and frequency. Telecommunications firms envisioned diamond resonators that could vibrate at 100 billion times per second, enabling unprecedented signal quality. Defense agencies explored diamond's potential for making more durable, high-performance equipment that could survive heat, radiation, and shock. The challenge was scale. Growing diamonds is fundamentally different from growing silicon ingots. Silicon can be melted, cast, and sliced into wafers like a loaf of bread. Diamond, by contrast, must be grown slowly in precisely controlled environments. This makes mass production complex. But companies began to adapt. Modular CVD reactors capable of growing multiple wafers simultaneously were developed, each controlled by computer systems that maintained stable gas compositions and temperatures. As techniques improved, growth defects decreased and wafer sizes increased, approaching the dimensions used in conventional chip fabrication. Cost, once the greatest barrier, began to drop. In the 1980s, producing a 1-inch diamond wafer was astronomically expensive. By the 2020s, advances in reactor design and process automation had brought costs down dramatically. A single large CVD chamber could grow multiple wafers overnight. Although still more expensive than silicon, diamond's performance advantages, higher power, speed, and heat resistance, were increasingly seen as worth the investment for specialized applications. Governments recognized the strategic implications. Diamond technology has dual-use potential. It can power civilian networks and research instruments, but it can also enhance military capabilities. Ultra-fast radar systems, radiation-resistant spacecraft electronics, and high-power battlefield communications all stand to benefit from diamond wafers. Consequently, research programs in the United States, Europe, Japan, and China began investing heavily in synthetic diamond production, treating it as a strategic material akin to rare earth elements or advanced semiconductors. In parallel, new industries emerged around diamond optics. Because diamond is transparent across ultraviolet, visible, and infrared wavelengths, it can serve as the perfect optical window for high-energy lasers, telescopes, and scientific instruments. Where traditional glass would warp, crack, or absorb too much heat, diamond windows remain stable. NASA and other space agencies began experimenting with diamond optics for telescopes and sensors designed to operate in the harsh vacuum and radiation of space. Perhaps most intriguingly, diamond resonators, tiny vibrating structures carved from diamond sheets, show promise for transforming communications. These resonators can vibrate at frequencies orders of magnitude higher than silicon counterparts, producing signals of unparalleled clarity. Defense agencies imagine them embedded in next-generation radios that remain operational under extreme conditions. Consumer technology companies envision them inside future smartphones, enabling crystal-clear calls and ultra-fast wireless data with minimal power consumption. The global race to scale diamond production has intensified. In some ways, it mirrors the early days of the Silicon Revolution. Just as the first transistor labs gave way to sprawling semiconductor fabs, today's diamond reactors could evolve into full-scale manufacturing facilities. Whoever masters this technology first stands to gain not only economically but also strategically. And yet, challenges remain. Defect control, uniform doping, and large-area single-crystal growth are still active areas of research. Scaling diamond production to the level of silicon will require innovations in reactor design, materials handling, and integration with existing semiconductor processes. But the direction is clear. Diamonds are moving from research curiosity to industrial foundation. The laboratories that once guarded their diamond samples as rare marvels are now designing systems to produce them by the hundreds. What was once a geological treasure is becoming a manufactured material, and in the process, it's redefining what technology can do. Part 7: Global Implications. Power, strategy, and industry. When silicon rose to dominance in the mid-20th century, it did more than revolutionize technology. It reshaped the global balance of power. Nations that mastered silicon chip fabrication gained disproportionate economic and strategic influence. Today, a similar shift is looming with synthetic diamonds, and governments, corporations, and research institutions around the world are paying close attention. The stakes are immense. Diamond-based technologies promise faster computing, more resilient infrastructure, and military systems capable of operating in environments where conventional electronics fail. Whoever controls the means to produce, refine, and deploy these materials could command critical advantages in everything from communication networks to space exploration. A strategic material emerges for decades. Diamonds were associated with luxury markets and industrial tooling, not national security. That perception is changing rapidly. Synthetic diamond wafers and devices have dual-use potential. They can drive commercial innovation but also enhance military capabilities. This duality places them squarely in the category of strategic materials, alongside semiconductors, rare earth elements, and advanced composites. Consider communications infrastructure. Modern high-frequency radar systems and satellite communications rely on materials that can withstand high power and harsh conditions. Diamond wafers can operate at temperatures exceeding 1,800 degrees Fahrenheit, handle 30 times the power of silicon, and resist radiation damage. For a military force operating in extreme environments, deserts, polar regions, deep space, diamond-based systems offer unmatched reliability. A single malfunctioning chip can jeopardize a satellite mission or radar array. Replacing silicon with diamond could make these systems not just more powerful, but virtually unbreakable. This potential has not gone unnoticed. In the United States, defense agencies have funded research into diamond electronics for high-power radar, secure communications, and space systems. In Europe, collaborative programs between research institutes and aerospace companies are exploring diamond optics and wafers for next-generation satellites. In Asia, countries like Japan and China are rapidly scaling up their diamond research capabilities, investing in both CVD reactor infrastructure and materials science talent. Economic shifts and industrial realignments on the economic front. The implications are equally profound. Silicon manufacturing has a deeply entrenched global supply chain, with production concentrated in a handful of regions. Synthetic diamond technology could disrupt this ecosystem. CVD reactors and HPHT presses can be operated in relatively compact facilities, potentially decentralizing production. This could reduce dependence on specific geographic choke points and redistribute manufacturing power. Companies that once specialized in mining or jewelry are rebranding themselves as high-tech materials firms. De Beers Element 6, originally focused on industrial diamond tools, now produces advanced synthetic diamonds for electronics and quantum applications. Startups in the US, Europe, and Asia are competing to develop proprietary reactor designs, faster growth rates, and better doping techniques. Venture capital, traditionally wary of heavy manufacturing, is beginning to flow into diamond technology firms. The shift is reminiscent of the early semiconductor era, when small groups of researchers turned laboratory breakthroughs into global industries almost overnight. The difference is that this time, the material is orders of magnitude tougher and more versatile than silicon. Companies that position themselves early in this new ecosystem may not just participate in a market, they may help define the technological landscape for decades. Space, energy, and infrastructure, one of the most transformative arenas for diamond technology, lies beyond Earth itself. Space is a brutally unforgiving environment. Temperature swings are extreme, radiation is intense, and maintenance is impossible once a device leaves orbit. Diamond's thermal conductivity, radiation hardness, and transparency make it a natural candidate for spaceborne electronics and optics. Imagine satellites with diamond-based processors that run at peak performance without cooling systems, or telescopes with diamond lenses that remain perfectly stable under cosmic radiation. Diamond's resilience could reduce launch mass, extend satellite lifespans, and enable missions to environments that currently destroy conventional hardware. Back on Earth, energy infrastructure stands to benefit as well. High-power transmission systems, renewable energy converters, and grid components all face thermal and mechanical stress. Diamond electronics could drastically increase efficiency, reduce maintenance costs, and improve reliability. In nuclear energy or fusion reactors, where temperatures and radiation levels push materials to their limits, diamond could act as both a heat sink and an electronic control substrate, something no other material can do simultaneously. Quantum and future computing, perhaps the most intriguing and potentially disruptive application, involves quantum technologies. Certain diamond defects, known as nitrogen vacancy, NV, centers, behave in ways that make them useful for quantum sensing, communication, and computation. These NV centers can detect magnetic fields at the nanoscale, act as stable qubits for quantum computing, or enable ultra-precise navigation systems that don't rely on GPS. Unlike fragile superconducting qubits, diamond NV centers can function at room temperature, making them more practical for deployment outside specialized labs. Nations that invest in large-scale production of high-purity, defect-engineered diamond wafers may gain a head start in quantum infrastructure. This is not a distant possibility. Research groups have already demonstrated NV-based quantum sensors in medical imaging, geological surveys, and defense applications. Scaling these technologies could transform fields from medicine to cybersecurity. Geopolitical competition. All of this sets the stage for a new kind of geopolitical competition, one centered not on oil or silicon, but on carbon in its most perfect form. Just as semiconductor manufacturing became a matter of national strategy, so too is diamond manufacturing capacity becoming a marker of technological sovereignty. Countries are quietly building domestic supply chains for diamond growth reactors, seeding technology, and specialized fabrication tools. Export controls may follow, just as they did for advanced lithography machines. Diplomatic discussions around standards and verification are likely to emerge as diamond-based systems enter sensitive industries like defense and finance. The space race offers a glimpse of this dynamic. Satellites equipped with diamond electronics would be more resilient to both environmental hazards and potential attacks. Communications networks built on diamond resonators could offer ultra-secure, high-speed links resistant to eavesdropping and jamming. Control over these capabilities would confer strategic advantages that extend far beyond economics. Environmental and ethical dimensions. Interestingly, the rise of synthetic diamonds also intersects with environmental and ethical debates. Natural diamond mining has long been associated with ecological destruction and human rights concerns. Synthetic production offers a way to bypass traditional mining, potentially reducing environmental impact and human exploitation. However, large-scale synthetic diamond production is energy-intensive, particularly in CVD reactors. The global race to produce super diamonds raises questions about energy sources, emissions, and regulatory oversight. Countries investing heavily in this technology must also address its environmental footprint to ensure that the new diamond age doesn't repeat the mistakes of the fossil fuel era. The rise of synthetic diamonds is no longer confined to research labs or niche industries. It's a geopolitical, economic, and technological phenomenon with far-reaching consequences. As production scales and costs fall, these brilliant lattices of carbon are poised to influence everything from global power structures to environmental policy. What began as a quest to mimic nature's hardest substance is turning into a race that could redraw the world's technological map. Part 8. Cosmic Origins Revisited. Diamonds between stars and science. Long before humans learned to shape carbon in vacuum chambers, long before diamonds glittered on crowns or cut through granite, their story began in the stars. Diamonds are not merely geological products. They are cosmic artifacts, fragments of stellar life cycles preserved in crystalline form. To fully grasp why the diamond is such a powerful material, and why humans are now mimicking cosmic processes to create super diamonds, we have to return to their celestial birthplace. The stellar foundry. The early universe contained no carbon. After the Big Bang, it was dominated by hydrogen and helium, with only trace amounts of lithium. Carbon, the element that forms diamonds, graphite, and life itself, had to be forged in stars. When massive stars approach the end of their lives, their cores become crucibles where helium atoms fuse under immense pressure and temperature. This process, known as the triple alpha reaction, produces carbon atoms. As these stars swell into red giants, they begin shedding material into space. Eventually, many explode in spectacular supernovae, scattering carbon-rich debris across the galaxy. This debris mixes with interstellar gas clouds, forming the building blocks of new stars, planets, and, in some cases, diamonds. Every natural diamond on Earth contains atoms that were born in the heart of a dying star billions of years ago. Some of this cosmic carbon didn't wait for Earth's mantle to reshape it. In the cold, low-pressure vacuum of space, under conditions utterly unlike those deep underground, carbon atoms sometimes arrange themselves into microscopic diamond lattices. These tiny diamonds are among the most common solid forms of carbon in the galaxy, floating through interstellar clouds and coating meteorites. Black diamonds from the sky. The most compelling evidence for cosmic diamond formation comes from a strange type of stone found not deep underground, but on the Earth's surface. Carbonado, also known as black diamond. Unlike clear, single-crystal gems, carbonado is opaque, porous, and composed of countless microscopic diamonds fused together. For centuries, carbonado was a mystery. It didn't occur in kimberlite pipes like regular diamonds, and its internal structure lacked the signatures of high-pressure formation. In the late 20th century, isotopic analysis and microscopic imaging revealed something astonishing. Carbonado did not form in the Earth's mantle. Instead, it likely formed in space during supernova explosions. In these violent events, carbon atoms collide and fuse in low-pressure environments, aggregating into clusters of tiny diamonds. Over time, these clusters accumulate, glue together, and eventually travel across space. At some point in Earth's history, meteorites carrying carbonado diamonds struck the planet, scattering black diamonds across regions of South America and Central Africa. These cosmic diamonds are tougher than natural single crystals, lacking cleavage planes that make regular diamonds vulnerable to splitting. Their structure inspired scientists to rethink their approach to diamond synthesis. If nature can make diamonds without extreme pressure, using energy, collision, and vacuum, perhaps human technology could do the same. This insight led to a fundamental shift in diamond research. Instead of only focusing on high-pressure, high-temperature, HPHT techniques that mimic the mantle, scientists began exploring low-pressure methods inspired by space. This is how chemical vapor deposition, CVD, emerged as a viable pathway. By bombarding gases in vacuum chambers, scientists could recreate the energetic but low-pressure conditions found in stellar environments, coaxing carbon atoms into forming diamond lattices just as they do between stars. Diamonds as cosmic time capsules beyond their physical properties. Diamonds also serve as time capsules of the universe. Some microscopic diamonds found in meteorites predate the formation of the solar system itself. These pre-solar diamonds carry isotopic signatures of the stars they came from, allowing astrophysicists to study stellar evolution in ways no telescope can achieve. Each tiny grain contains a unique fingerprint of a distant star's life and death. When scientists analyze these diamonds with spectrometers, they detect unusual ratios of carbon, nitrogen, and noble gases, chemical evidence of their extraterrestrial origin. These ratios can't be produced by Earth's geology. In effect, diamonds are messages from ancient stars, preserved for billions of years and delivered to Earth via cosmic messengers. This celestial perspective is more than scientific trivia. It has directly influenced how we engineer diamonds today. Researchers studying carbonado structure realized that its multi-crystal network makes it almost impossible to cleave, unlike single-crystal gems. Inspired by this, modern synthetic methods now aim to grow polycrystalline diamond wafers, sheets made up of countless crystals fused together. These wafers combine diamonds' hardness and thermal conductivity with extraordinary toughness, making them ideal for high-stress environments like space vehicles, fusion reactors, or battlefield electronics. Space technology meets diamond technology. The cosmic connection comes full circle when we look at how diamond technology is now fueling space exploration. Diamonds' radiation resistance and optical transparency make it a prime candidate for spaceborne sensors, communication arrays, and telescope optics. NASA and other space agencies are experimenting with diamond windows for instruments that must endure ultraviolet radiation and extreme temperature shifts without warping. Moreover, Diamond-based electronics can operate reliably in the vacuum of space, where cooling systems are impractical. A satellite with diamond processors wouldn't need heavy heat sinks, reducing launch weight and increasing mission duration. Future spacecraft may even rely on diamond thrusters and power systems built to survive the intense radiation belts of other planets, an echo of the diamond's stellar origin, now applied to exploring the stars they came from. Philosophical resonance: there is something profoundly poetic about this technological arc. Diamonds were born in stars, traveled through space, and eventually became part of a young planet. Billions of years later, intelligent beings on that planet learned not only to understand these stones but to recreate and improve them, using techniques inspired by the same cosmic processes that made them in the first place. It is as if humanity, in learning to grow super diamonds, is closing a cosmic loop. From star to stone, from stone to science, from science to the stars again. This cosmic perspective also reframes diamonds not just as tools or materials, but as bridges across time. When engineers grow diamonds in a reactor, they are not merely manufacturing a substance. They are participating in a process that began in the cores of long-dead stars. Each synthetic diamond is, in a sense, a continuation of stellar evolution, shaped not by gravity and fusion, but by human hands and electromagnetic fields. As research delves deeper into both the cosmic and atomic dimensions of diamond, scientists are discovering not just how to make diamonds, but why the universe makes them in the first place. This dual lens, looking outward to the stars and inward to the lattice, is driving innovations that neither astronomy nor materials science could achieve alone. The age of super diamonds is, in many ways, a cosmic collaboration between the universe and human intelligence. Part 9. The Turning Point. Breakthrough discoveries and leaps forward. Every technological revolution has a moment when scattered discoveries converge into a clear trajectory. A point at which theory, experimentation, and necessity align to create irreversible momentum. For synthetic diamonds, this turning point came during the late 20th and early 21st centuries. What had once been an experimental curiosity became a strategic priority across industries. Scientific breakthroughs in growth techniques, structural control, and application design began to unlock capabilities that nature itself could not offer. The hybrid approach, HPHT meets CVD. The first breakthrough came from combining two previously separate methods: high pressure, high temperature, HPHT, synthesis and chemical vapor deposition, CVD. For decades, these approaches had been viewed as alternatives. HPHT was excellent for producing bulk crystals quickly but limited in purity and shape. CVD offered unprecedented control over lattice structure and impurities but was slower and initially produced smaller crystals. Researchers realized that using HPHT to create seed crystals, and then CVD to grow them further, could combine the strengths of both methods. HPHT provided the initial template, a rugged, defect-resistant starting point. CVD then refined and expanded that structure, layer by layer, allowing scientists to grow large, high-purity diamonds in controlled shapes. This hybrid technique dramatically improved both speed and quality. Instead of waiting weeks to grow a large crystal via CVD alone, scientists could begin with a robust seed and achieve their desired size in just a few days. This method is now a cornerstone of modern diamond wafer production. Carbonado as a blueprint. At the same time, renewed research into carbonado, the black diamonds believed to be of cosmic origin, yielded surprising insights. Scientists discovered that carbonado's multi-crystal structure isn't a defect, it's a strength. Unlike single-crystal diamonds, which have cleavage planes along which they can split, carbonado's tangled network of microscopic crystals makes it extremely tough. It can withstand shocks, impacts, and pressures that would fracture even the purest gem-quality diamond. This understanding inspired engineers to grow polycrystalline diamond wafers using CVD techniques. By carefully controlling temperature, pressure, and gas composition, they learned to encourage multiple growth fronts that fuse together seamlessly. The result: wafers with the thermal and electronic advantages of diamond, combined with structural toughness far beyond what natural single crystals could offer. Polycrystalline wafers quickly found applications in high-stress environments, from aerospace components and deep drilling equipment to military systems exposed to extreme temperatures. They were also well-suited to high-power electronics, where reliability under stress is as important as performance. Low-defect, large-area growth. Another turning point came with advances in low-defect, large-area growth. One of the earliest challenges in diamond wafer production was maintaining crystal quality over large surfaces. Defects such as grain boundaries, dislocations, and impurity clusters could disrupt both electronic and thermal performance. Early wafers often contained too many imperfections to be useful in precision electronics. To solve this, researchers refined microwave plasma CVD techniques. By tuning the plasma parameters, power, frequency, pressure, and gas ratios, they created growth environments that stabilized diamond formation across wide areas. This allowed the production of 8-inch wafers with unprecedented uniformity. While still expensive, these wafers represented a leap toward commercial-scale applications. At the same time, new in-situ diagnostic tools allowed scientists to monitor growth in real time. Using spectroscopic sensors and high-resolution cameras, they could detect impurities or structural defects as they formed, adjusting conditions on the fly. This feedback loop drastically reduced waste and improved yield, an essential step toward industrial scalability. Breakthroughs in doping control. Diamonds' electronic properties hinge on precise impurity control, especially the introduction of boron for semiconductivity. For years, doping diamond during growth was inconsistent. Boron atoms would cluster unevenly or fail to integrate properly, leading to unpredictable electrical behavior. The breakthrough came when researchers learned to modulate boron introduction dynamically during CVD. By synchronizing gas flows and microwave pulses, they could incorporate boron atoms evenly across the growing lattice. This allowed the creation of uniform p-type diamond layers, essential for building reliable transistors and diodes. Further innovations explored n-type doping, which is far more difficult in diamond than p-type. While this remains a frontier challenge, progress in introducing phosphorus and other elements has opened pathways to full diamond-based electronic circuits, not just isolated components. Diamond resonators and quantum defects. Another major leap came not from structural control, but from exploiting defects intentionally. Researchers discovered that certain nitrogen vacancy, NV, centers in diamond behave as stable quantum systems, capable of storing and manipulating information at the level of individual electrons. Unlike delicate superconducting qubits, NV centers can operate at room temperature, making them ideal for quantum sensors, communications, and potentially computing. This realization transformed what were once considered imperfections into features. Laboratories began growing diamonds with engineered defect densities, tailoring NV centers for specific applications. Quantum sensors based on NV diamonds are already being used in fields such as medical imaging, geology, and defense. Cross-disciplinary convergence. Perhaps the most important turning point was not a single discovery, but the convergence of disciplines. Diamond research drew in physicists, chemists, material scientists, engineers, astronomers, and defense strategists. Each brought new perspectives. Astronomers revealed how diamonds form in stars. Chemists refined growth techniques. Engineers developed reactors. Defense agencies funded applications. Physicists explored quantum behavior. This convergence accelerated innovation. Problems that once stalled progress were solved by insights from unexpected fields. Diamond technology stopped being a niche material science project and became a multi-sector endeavor with momentum on several fronts simultaneously. From curiosity to imperative. By the early 21st century, these breakthroughs had collectively shifted synthetic diamonds from a scientific curiosity to a technological imperative. The material's potential to outperform silicon, its cosmic inspiration, and its adaptability across fields made it impossible to ignore. Governments began funding coordinated programs, industries built pilot production facilities, and universities established diamond research centers. What had once been a handful of specialized labs grew into a global network pushing the boundaries of what diamond could do. The story of synthetic diamonds reached a tipping point when the pieces, growth control, structural insight, quantum defects, hybrid synthesis, and interdisciplinary collaboration locked together like carbon atoms in a lattice. From that point on, the field was no longer asking, can we make diamonds? But how far can we go? The breakthroughs didn't just mimic nature, they went beyond it, opening possibilities that even the stars had not achieved. Part 10. The Industrial Acceleration. Diamond in the real world. By the time the key scientific breakthroughs aligned, the global landscape was ready for a massive industrial acceleration. Synthetic diamond technology, once confined to academic laboratories and specialized defense projects, began entering the broader industrial ecosystem. What followed was not a sudden explosion, but a steady, compounding expansion. As manufacturing capacity grew, applications diversified, and industries started to reimagine products and systems through the lens of diamond's unique capabilities. A new class of manufacturing facilities, traditional semiconductor fabs, were never designed to grow diamonds. Silicon is melted, cast, sliced, and etched. Diamond must be grown, atom by atom, under precise plasma conditions. This required a new generation of production facilities that blended semiconductor cleanroom standards with the high-energy reactors of material science labs. Companies began building modular CVD growth farms, facilities containing hundreds of reactors arranged in tightly controlled environments. Each chamber grew one or multiple diamond wafers under continuous computer supervision, with plasma parameters monitored in real time. Artificial intelligence systems adjusted gas flows and temperatures to maximize uniformity and reduce defects. These diamond fabs did not replace silicon plants overnight. Instead, they emerged alongside them, often in specialized industrial zones or near research institutions. Governments offered incentives and subsidies to build early facilities, recognizing the strategic value of mastering this technology. What started as pilot projects in Japan, the US, and Europe rapidly expanded into multi-billion-dollar manufacturing centers. Electronics. Beyond silicon's limits, the electronics industry was among the first to seize the new opportunities. Silicon's limitations had long been known. As transistors shrink and power demands rise, heat management becomes a critical bottleneck. Diamond's extraordinary thermal conductivity, about 5 times that of copper, offered a solution. Initially, companies used diamond heat spreaders to dissipate heat in high-power devices like 5G base stations, radar arrays, and laser systems. This alone delivered dramatic performance improvements, enabling higher frequencies and longer device lifespans. But the real acceleration came when diamond wafers themselves began replacing silicon in specialized applications. Power electronics firms produced diamond-based transistors and diodes capable of operating at 10 times the power density of conventional devices. Aerospace and defense systems adopted diamond circuits that could function in extreme environments without heavy cooling systems. While diamond couldn't immediately compete with silicon for consumer microchips due to cost and fabrication differences, it dominated niche high-performance markets, just as gallium nitride, GaN, and silicon carbide, SiC, had done earlier. In radar, satellite communications, fusion reactors, and electric vehicle power systems, diamond-based components began outperforming everything else. Optics and photonics in parallel. Optics and photonics industries embraced diamond's broad-spectrum transparency and exceptional durability. Traditional optical materials deform or absorb energy under extreme conditions, but diamond remains stable from ultraviolet through infrared wavelengths. High-energy laser systems integrated diamond windows and lenses that could withstand enormous thermal loads without distortion. This allowed for more powerful, longer-lasting laser operations, essential for industrial cutting, defense systems, and scientific research. Space agencies adopted diamond-coated sensors and telescope components for missions beyond Earth's protective atmosphere. These optical elements resisted radiation damage and micrometeoroid impacts far better than glass or quartz. The result? Lighter, more reliable instruments capable of operating for decades in orbit. Energy systems and infrastructure. The energy sector also began to transform. Diamond-powered devices offered unprecedented efficiency in converting and transmitting electricity. High-voltage converters based on diamond semiconductors operated at higher temperatures and voltages with lower losses, making them ideal for renewable energy grids and electric vehicle infrastructure. In fusion research, diamond was adopted as both a structural material and a sensor platform inside experimental reactors. Its ability to withstand neutron bombardment and extreme heat made it indispensable in environments that would destroy conventional materials within seconds. Utilities and grid operators began experimenting with diamond-based switchgear and control systems designed to last decades without failure. In regions where replacing infrastructure is costly or dangerous, offshore wind farms, desert solar arrays, or Arctic research stations, diamond electronics offered reliability that silicon simply couldn't match. Quantum and sensing applications, perhaps the most futuristic wave of industrial acceleration, came from quantum technologies. Diamonds containing engineered nitrogen vacancy, NV centers, began appearing in commercial sensors. These devices could detect magnetic fields, temperature changes, and molecular structures with extraordinary precision, even at room temperature. Hospitals used diamond-based sensors for non-invasive medical imaging, detecting subtle changes in electromagnetic fields generated by the human body. Geologists deployed portable NV sensors to map underground structures, while defense agencies used them for stealth detection and secure navigation that didn't rely on GPS. At the same time, quantum communication companies began experimenting with diamond-based quantum repeaters, essential components for future quantum internet infrastructure. These devices exploit NV center stability to store and transmit quantum information over long distances, something no other solid-state system had achieved at scale. Automotive and aerospace. The automotive and aerospace sectors, always hungry for lightweight and heat-resistant materials, embraced synthetic diamonds for critical components. High-power diamond electronics were integrated into electric vehicle inverters, drastically improving efficiency and reducing cooling requirements. Aircraft manufacturers used diamond composites in avionics and radar systems, allowing them to operate in harsh flight conditions with minimal maintenance. Diamond-based sensors monitored structural integrity in real time, detecting microscopic cracks or temperature spikes long before they became critical. For space exploration, diamonds' radiation resistance and optical stability made it a key enabler. Satellites equipped with diamond processors and optics became more compact and resilient. Probes destined for Venus, Jupiter's radiation belts, or interstellar missions relied on diamond systems that could endure where silicon would melt or fail within minutes. Economic ripple effects. As these applications spread, the economic landscape began to shift. Entire new supply chains formed around diamond reactor manufacturing, wafer processing, defect engineering, and device fabrication. Specialized companies emerged to supply gases, seeds, plasma generators, and surface polishing systems. The cost curve for synthetic diamond production began to bend downward. Once prohibitively expensive, large wafers were now being produced with increasing yield and decreasing defect rates. Economies of scale took hold. As demand grew, investment flowed, accelerating innovation and reducing costs further, a feedback loop reminiscent of the early semiconductor boom. While diamond would not replace silicon across all markets, it became an indispensable complement in high-performance domains. Just as silicon enabled the information age, diamond began enabling the extreme performance age, where devices operate in conditions that once seemed impossible. The industrial acceleration of synthetic diamonds represents a new technological era. What started in deep Earth and distant stars is now reshaping factories, energy grids, satellites, vehicles, and medical systems. Diamonds are no longer just symbols of permanence. They are becoming infrastructural foundations of the future. Part 11. Ethical, environmental, and societal impacts of the Diamond Age. Every technological revolution carries not only scientific breakthroughs and economic opportunities, but also ethical dilemmas, environmental consequences, and societal transformations. The rise of synthetic diamonds is no exception. While it offers cleaner alternatives to mining and paves the way for extraordinary advancements, it also introduces new questions about energy use, equity, labor, and control. The Diamond Age, like the industrial revolutions before it, is as much a social and political story as it is a technological one. The decline of traditional mining. For centuries, the diamond industry was defined by mining, a process fraught with environmental destruction, geopolitical tension, and human rights abuses. Open-pit mines scar landscapes, consume vast amounts of water, and generate massive waste. In certain regions, diamond mining has also fueled conflict economies, financing armed groups through the trade in so-called blood diamonds. Synthetic diamonds promise to undermine this legacy. By producing diamonds in controlled laboratory environments, industries can bypass destructive mining operations altogether. No mountains are removed, no rivers diverted, and no forced labor camps established. Environmental groups have hailed synthetic diamonds as a potentially revolutionary shift, comparable to the way renewable energy challenges fossil fuels. Already, some nations heavily reliant on natural diamond exports are facing economic adjustments. Botswana, Namibia, and Russia, historically dominant players in the diamond trade, are seeing their market share erode as lab-grown diamonds become cheaper, purer, and more customizable. Jewelry companies increasingly market conflict-free lab diamonds, reshaping consumer perceptions of luxury. However, the decline of mining is not without consequences. In some countries, diamond revenues fund public services and infrastructure. A rapid industrial shift without economic transition plans could destabilize communities that depend on mining jobs. Ethical progress in one arena may create new social challenges in another. Energy demands and environmental footprint. While synthetic diamonds avoid the environmental damage of mining, they are not impact-free. Growing diamonds using CVD or HPHT methods is energy-intensive, often requiring sustained high temperatures and plasma generation for days or weeks. The environmental impact of synthetic diamond production depends heavily on the source of electricity. When powered by renewable energy, synthetic diamond production can achieve a far smaller carbon footprint than mining. But when powered by fossil fuels, the emissions can rival or exceed traditional methods. This has prompted policymakers and companies to integrate renewable energy sources directly into diamond fabs, turning them into net zero or even net negative facilities by combining diamond growth with solar, wind, or geothermal power. Some forward-thinking companies are experimenting with closed-loop gas systems and waste heat recovery, using the byproducts of one reactor to fuel another. Others are building diamond fabs in regions with abundant green energy, such as Iceland or parts of Canada, to minimize environmental impact. Ethical manufacturing and labor synthetic diamond production also reshapes labor dynamics. Traditional diamond mining relies on large, often low-wage labor forces engaged in physically demanding and dangerous work. Synthetic diamond manufacturing, by contrast, depends on highly skilled technicians, engineers, and scientists. This shift has both positive and negative effects. It eliminates many exploitative labor practices associated with mining and raises working conditions. But it also concentrates value creation in high-tech sectors, potentially excluding communities that lack access to education or technical training. Governments and organizations are beginning to address this by launching training programs to prepare workers for jobs in the diamond technology sector, from reactor maintenance and wafer polishing to quantum sensor calibration. If done well, this transition could elevate entire communities into new technological economies. If neglected, it risks widening inequality between regions that adapt and those left behind. Access, control, and inequality as synthetic diamonds become central to strategic technologies, from high-power electronics to quantum communication. Questions of access and control become unavoidable. Who owns the reactors? Who controls the supply chains? Which nations dominate the intellectual property and manufacturing capacity? Much like semiconductors, diamond technology could become highly concentrated, with a handful of countries or corporations controlling critical infrastructure. This concentration could exacerbate global inequalities, giving technologically advanced nations immense leverage over others. Export controls, trade disputes, and technological embargoes could become as contentious as those surrounding advanced lithography machines today. Conversely, the modular and decentralized nature of CVD reactors could also allow for broader participation. Unlike semiconductor fabs, which require massive capital and specialized lithography equipment, Diamond reactors can be built at smaller scales and distributed more widely. If managed inclusively, this could democratize access to advanced materials. The path society takes depends on policy decisions made now. International agreements, export frameworks, and collaborative research programs could help distribute benefits more equitably, or, if ignored, could entrench new forms of technological monopolies. Cultural shifts and perception. Synthetic diamonds are also changing cultural narratives. For centuries, natural diamonds have been marketed as symbols of rarity and permanence, their value tied to geological time and scarcity. Lab-grown diamonds challenge this mythology. When a flawless diamond can be grown in a week, what does rarity mean? Jewelry markets are already adapting. Younger generations, more environmentally and ethically conscious, increasingly prefer lab-grown diamonds precisely because they reject the extractive model. High-end designers now emphasize transparency, traceability, and technological elegance rather than geological mystique. Beyond jewelry, diamonds are becoming symbols of innovation rather than luxury. A diamond lens on a space telescope or a diamond processor in a fusion reactor embodies a different kind of cultural meaning, one tied to human ingenuity rather than natural scarcity. Ethical use of advanced applications. Finally, the rise of diamond-based technologies raises profound questions about how these tools are used. Diamond electronics could make defense systems more resilient, but they could also fuel new arms races. Quantum sensors could revolutionize medicine, but also enable surveillance of unprecedented subtlety. Ethical frameworks must evolve alongside the technology. Transparent governance, international cooperation, and public debate will be essential to ensure that the diamond age benefits humanity broadly, rather than deepening existing divides or enabling destructive competition. The rise of synthetic diamonds is reshaping not only industries and technologies, but also values, power structures, and cultural narratives. If managed wisely, this transformation could replace exploitative extraction with sustainable innovation, democratize access to powerful technologies, and help humanity thrive in environments that were once unreachable. If mishandled, it could entrench new inequalities, consume vast energy resources, and amplify global tensions. The diamond age is not just about brilliant materials, it is about how society chooses to wield them. Part 12. The Future Horizon. Visions, scenarios, and speculation. The story of diamonds began billions of years ago in the hearts of ancient stars. It continued deep within the Earth's mantle, where pressure and heat shaped carbon into brilliant lattices. Then, in human laboratories, those cosmic and geological processes were recreated and refined. Now, as the diamond age matures, attention turns to the future. How far can this technology go, and what kind of world might emerge from it? The possibilities range from pragmatic to profound. Some scenarios involve incremental technological progress. Others envision civilizational shifts built on diamonds' unique properties. A new technological substrate. Just as silicon became the physical substrate for the digital revolution, diamond could become the substrate for the extreme performance age. Its thermal conductivity, structural strength, and electronic versatility make it ideal for technologies that operate under conditions previously considered impossible. In the near future, diamond wafers may become standard components in power infrastructure, aerospace systems, radar arrays, and high-frequency communications. Diamond processors could handle heat loads that would melt silicon, enabling ultra-dense computing systems for AI, weather prediction, or defense. Beyond electronics, diamond optics may underpin new kinds of high-energy lasers, particle accelerators, and deep space telescopes. Their ability to remain stable under intense radiation and thermal stress opens pathways to instruments that can peer deeper into the universe and operate for decades without maintenance. Terraforming and extreme environments. One of the most striking applications lies not on Earth, but on other worlds. The ability to build electronics, optics, and structural components out of diamond could make previously uninhabitable environments accessible. Imagine a probe landing on Venus, where surface temperatures exceed 450 degrees Celsius and pressures crush most materials within hours. Diamond-based electronics and sensors could survive there for months or even years, sending back data from a planet long considered too hostile for long-term exploration. Similarly, Jupiter's radiation belts, which would fry conventional spacecraft, could be navigated by probes shielded and powered by diamond systems. Human colonies on the Moon or Mars might rely on diamond-based energy infrastructure, resistant to temperature swings and radiation storms. In more speculative scenarios, terraforming technologies could use diamonds' unique properties to manage energy flows on a planetary scale. High-power diamond-based converters might regulate solar energy, drive magnetic field generators, or stabilize environmental systems over decades of continuous operation. The quantum diamond age. The quantum properties of diamond, especially nitrogen vacancy, NV, centers, suggest a future in which quantum technologies become integrated into everyday infrastructure. Unlike fragile superconducting systems, NV-based quantum devices can operate at room temperature, making them more practical for widespread deployment. Quantum communication networks could use diamond repeaters to transmit secure, unhackable data across continents and between satellites. Hospitals could employ diamond quantum sensors for real-time brain imaging, allowing neurologists to map neural activity at unprecedented resolution without invasive procedures. Civilian navigation systems could shift away from GPS entirely, using diamond quantum magnetometers to navigate based on Earth's magnetic fields with centimeter-level accuracy, even underground or underwater. On the computing front, if scalable methods for NV-qubit entanglement and error correction are developed, diamond could host robust, room-temperature quantum computers. These wouldn't just accelerate existing tasks. They could open entirely new domains of simulation, optimization, and cryptography. New architectures and devices. Diamond's versatility allows for devices and architectures that don't fit existing technological categories. Future engineers might design hybrid devices where a single diamond wafer integrates optical, electronic, and quantum components. For example, a single diamond chip could generate, process, and transmit information using photons, electrons, and quantum states simultaneously. This could lead to self-contained supersystems, sensors that analyze their environment, compute optimal responses, and communicate results without external modules. Such systems would be ideal for autonomous spacecraft, swarm robotics, or next-generation military platforms, where reliability, power efficiency, and multifunctionality are essential. Economic and strategic realignment. If diamond becomes the dominant substrate for critical technologies, global economic and strategic systems may realign, much as they did during the Silicon Revolution. Nations that master diamond manufacturing and device integration will likely command disproportionate influence over industries ranging from defense to energy to communications. New diamond economies may emerge, based not on mining but on knowledge, reactor capacity, and defect engineering expertise. Countries investing early in research and infrastructure could become technological hubs for the diamond age, while those that lag may find themselves dependent on imported advanced materials. At the same time, the modularity and scalability of CVD reactors mean that smaller nations, cities, or even corporations could build localized production facilities. This could lead to a more distributed technological landscape with multiple centers of diamond innovation, or, conversely, fierce competition over intellectual property and production know-how. Environmental regeneration. Synthetic diamonds also hold potential for environmental regeneration. Their unmatched durability and performance could enable long-lived renewable energy infrastructure that minimizes waste. Diamond-based desalination systems, high-efficiency solar converters, and ultra-stable environmental sensors could play key roles in managing Earth's changing climate. In one speculative scenario, diamond-based technologies enable massive global carbon capture operations, where reactors convert atmospheric CO2 into diamond structures directly. This would be both a technological solution and a symbolic reversal, turning excess greenhouse gases into the most stable form of carbon known. Cultural and philosophical shifts. Technological revolutions often bring cultural transformations. As synthetic diamonds become ubiquitous, in satellites, hospitals, quantum networks, and everyday devices, they may lose their status as luxury symbols and instead represent human mastery of nature's deepest structures. In a future where growing a flawless diamond is as routine as printing a circuit board, society may view these crystals less as rare treasures and more as universal building blocks, like steel in the industrial age or silicon in the digital age. This shift could influence art, architecture, and even philosophy. The notion that humanity can recreate stellar processes on Earth might reshape how people think about their place in the cosmos. Synthetic diamonds could become symbols of continuity between cosmic forces and human creativity. Risks and unknowns, of course. The diamond age is not guaranteed to unfold smoothly. Concentration of production power could lead to new geopolitical tensions. Diamond-based weapons and surveillance systems could spark arms races. Quantum networks, while secure, could disrupt existing communication and intelligence paradigms. Environmental benefits depend on clean energy sources. Otherwise, diamond production could add to global emissions. Furthermore, unforeseen technical challenges may emerge. Defect engineering at quantum scales, large area wafer uniformity, or reactor stability could prove more complex than expected. History shows that revolutionary technologies often advance unevenly, sometimes in leaps, sometimes in stalls. An open horizon, the future of diamonds is, fittingly, as hard to shape as the material itself. Yet the trajectory is clear. Humanity is learning not only to replicate, but to surpass natural processes, turning carbon into one of the most versatile technological platforms ever known. Whether the diamond age becomes an era of distributed innovation and environmental regeneration, or one of concentration and competition, will depend on choices made in the coming decades, choices about energy, governance, ethics, and collaboration. One thing is certain. The brilliance of diamonds will no longer be confined to jewelry or deep earth. It will shine through power grids, spacecraft, quantum networks, and environmental systems, shaping the future in ways both practical and profound. Part 13, Conclusion. The diamond age realized from the fusion furnaces of dying stars to the pressurized depths of the Earth's mantle, from laboratory reactors to quantum communication networks. The story of diamond is one of transformation across scales, cosmic, geological, technological, and cultural. What began as atoms forged in stellar cores has become a platform for human innovation unlike any other. A cosmic material, reclaimed diamonds were among the first solids to form in the young universe, crystallizing from carbon scattered by supernovae. They traveled across interstellar space, embedding themselves in meteorites long before the Earth existed. Then, within our planet's mantle, they grew again, this time under crushing pressure and heat, waiting for volcanic eruptions to carry them upward. For most of human history, diamonds were passive objects of desire. People mined them, traded them, adorned themselves with them, and assigned them symbolic power. Their brilliance was admired, but their internal structure, their atomic logic, remained hidden. The turning point came when scientists unlocked the lattice, learning how to grow and shape diamond intentionally. In doing so, humanity did more than copy nature. It reclaimed a cosmic process, bringing stellar and geological forces under deliberate control. From curiosity to foundation, initially, synthetic diamonds were scientific curiosities. Tiny crystals grown in cumbersome machines, useful mainly for cutting tools. Over decades, research revealed their unparalleled physical properties, inspiring new techniques to grow larger, purer, and more complex structures. As HPHT and CVD methods matured, as defect control improved, and as interdisciplinary collaborations flourished, diamonds transitioned from rare geological anomalies to engineered materials. They moved from jewelers' vaults to clean rooms, energy grids, and orbital platforms. Today, synthetic diamonds form the backbone of emerging technological systems. Ultra-high-power electronics, quantum sensors, extreme environment optics, next-generation communications, and perhaps even planetary engineering. Where silicon enabled the digital age, diamond may enable the extreme performance age. An era defined not by where humans can live, explore, and build, but by the limits of their imagination. Ethics and environment. Unlike past industrial transformations, the diamond age arrives with an opportunity to choose differently. Traditional diamond mining has scarred landscapes and communities. Synthetic production offers the chance to separate value from extraction. But this promise depends on energy choices and governance. Diamond reactors powered by renewables could become engines of environmental regeneration. Powered by fossil fuels, they could deepen the very crises they might otherwise help solve. Similarly, diamond technologies can empower societies or entrench power. Modular, distributed production could democratize access. Concentrated ownership could create new monopolies. The ethical trajectory is not inherent in the material, it lies in human decisions. The symbol evolves culturally, the diamond's meaning is shifting. No longer solely a symbol of rarity or romantic permanence, it has become a symbol of human capability, bridging the cosmic and the technological. A diamond in the future may not sit in a ring but in a spacecraft's core, a fusion plant circuitry, or a quantum network's repeater. Its sparkle will no longer be lit only by sunlight but by electromagnetic fields, laser pulses, and cosmic rays. The mythology surrounding diamonds is evolving. They are no longer treasures to be found. They are tools to be forged. An open future, the trajectory of the diamond age is not predetermined. It will be shaped by policies, energy choices, cultural narratives, and global collaboration. If guided wisely, it could help address some of humanity's most pressing challenges. Energy sustainability, environmental stability, technological resilience, and exploration beyond Earth. If mishandled, it could amplify inequalities, accelerate arms races, or create new ecological strains. What makes this moment extraordinary is that humanity is no longer a passive participant in the diamond story. It is now an active author. The same carbon atoms that once drifted through space are now structured by human minds and machines, forming the physical foundation for new possibilities. A glimpse backward and forward, consider this. Every diamond, whether natural or synthetic, is a time traveler. The atoms within it were created billions of years ago, long before the Earth, the Sun, or life itself. When humans grow diamonds today, they are not inventing something new. They are continuing a process that began in the stars. The difference is that the stars acted blindly, while humanity acts with intention. In that sense, the diamond age is not merely about a material, it is about a shift in agency. It represents the moment when humanity learned to take one of the universe's most ancient, enduring structures and reshape it for its own future. The brilliance of the diamond has always captivated the human eye, but its true brilliance lies in its structure, in the story it tells. A story that stretches from supernovae to laboratories, from volcanoes to vacuum chambers, from adornment to infrastructure. The diamond age has begun. Its trajectory will reflect not just the hardness of carbon, but the clarity of human vision.